So where are we? So if you notice, this is not the title of the talk that was in the program. I decided to ditch that. And kind of, I want to do something that was a little more advanced than a ROP 101, but I'm going to still try to start from the basics. So if you don't know anything about code reuse attacks at all, you can catch on pretty quickly. So that's ROP 101.5. This is going to go fast, so please, please, please stop me with questions if you don't understand anything. Okay? With that said, let's go. So why should we care about ROP? Many of you know ROPs being used in some of the most cutting-edge attacks. All of your APT attacks tend to use ROP, tend to use things that get around ASLR, tend to use things that get around EMET, things like that. But there's really three words that you never want to see when you're reading a CV. Those. Arbitrary code. This is the holy grail. This is the attacker has control of your system. You do not want this. Problem is, it's kind of hard to protect against these advanced ROP attacks. Just in the last 2 years, this is CVEs, arbitrary code execution, that have been exploited in the wild as ODAs with ROP. These are all heap-based buffer overflows, pretty much, from IE Flash. IE Flash and WRAM, sorry. So, this is 11 CVEs I found in just a really quick search that I saw were being actively exploited with ROP. Why exactly do we need ROP? I mean, this is a somewhat advanced topic. You guys have seen code reuse, but where did we come from? Well, it used to be easy. Attacker could just find some buffer, a stack buffer, a heap buffer, somewhere where he can write data. This is a programming error, but unfortunately everything's written in C still, so there's plenty of them to go around. Attacker overwrites some bit of memory in the stack on the heap, overwrites a return address or some code pointer, and points right back into his little shellcode that he injected. This is pretty easy, been around since 1996. If you haven't seen this, go read the FRAC article. But why don't we still use this? Well, we can't, and I'll go through explaining why. First, a quick demo on code protection. I apologize if anyone's afraid of x86 code. You will see some. I will explain it. Don't worry. So here's a really simple two functions. We've got a main function, and we've got some vulnerable function. Now, this vulnerable function takes some attacker-supplied data and store copies it. Now, if any of you know application security, you know this is a really bad idea. Because store copy simply copies data until it finds a null bucket. If an attacker is supplying the data, he can overrun whatever buffer you're copying this data into and perform as attacker. So this is how it goes. Normal execution, the program is going to call this vulnerable function. Return address goes on the stack on the left. We put a base pointer, and the store copy is called, which copies those orange bytes into a stack buffer. Okay? Simple enough. This is what's supposed to happen. The buffer is only 2 stack words. Well, then we go back through, pop things off, return, and when we get to the return address, it's still the same. This is what you want. You want the return address to point where you came from. Well, what happens when our attacker comes? Same call to multiple function, same pushing the return pointer on. But now we have the attacker overwriting all of this red code. This is on the stack. He overwrites what was the buffer. He overwrites the old RBP, which is the base address. Don't worry about it. He overwrites the return address, which is the important bit. That's where code is going to go after this vulnerable function finishes running. And he injects some shellcode. That's the random looking bytes down there. And yes, it's a proper x86 shell. So, as the program goes back through, after the attacker's injected his buffer overflow, the program's going to get to this return. And the return simply takes whatever's on top of the stack. In this case, the address of the stack shellcode, and jumps it. You can see where this is going. Now, the stack is actually executing instead of the program. This is bad. In this case, we get the NSH running. So, that's your really super simple buffer overflow. This is what we used to do back in the good old days. However, people are smart, figure it out. We don't need the stack heap to be executable. This is stupid. Why is the stack executable? It's data. It is never code. So, along came write XOR execute, or data execution prevention, depending on if you're in the Linux or Windows. This was pioneered by the PAX team in Linux in 2000 and in Windows in 2004. And all it is it was originally a set of kernel patches, now it's implemented in hardware, so the processor supports this. It allows the program to mark some pages as executable, this is my code, and other pages, memory pages, are, this is my stack, this is my heap. These pages are read and write, but not execute. So this prevents something from being both writable, so that the attacker can inject code, and executable, so the attacker can run. So we leave the code executable, we make the stack and the heap writable. This is great. This takes care of your simple buffer overflows, because the attacker now can't simply redirect control flow back into the stack. Questions? All right. So where do we go from here? Well, attackers are smart. So we have code reuse attacks. Attackers figured out, I don't need to inject code into the program. I can simply reuse all of that code. So all of this code that's marked executable in the red, I'll just reuse that code before my attack. And so this started out this simple attack called return to libc. This attack, rather than reusing stuff in the program itself, usually reused libc functions. Functions like execve. And so to do this, you had to put the parameters that you want for your exec call, or whatever other call you wanted, onto the stack, and then return into the beginning of a libc function, rather than to where we're intending to go. So it looks kind of like this. The attackers put on the buffer as before, but now this return address is pointing at, well, in this case, the program linkage table. Simply libc functions. So in this case, the attacker wants to run system with the parameter bin sh. So the attacker goes and finds bin sh somewhere in the program or somewhere in a library that's loaded and puts a pointer to that on the stack. As you can see, that's what the third value on the stack is. And returns straight to system. So system's going to pick up this parameter off the stack and it's going to execute bin sh. Great. This is pretty easy to do in the 32-bit world because parameters are actually passed on the stack. If you're not familiar with calling conventions, 32-bit calling convention in Linux is, hey, let's put parameters on the stack, unless you're using some sort of faster calling convention with registers. On 64-bit, this got more complicated because now all of the parameters to your libc functions are passed in registers. The attacker only has control over the stack, or maybe the heap and this stack. Just assume the attacker has control over the stack. So if we can't put parameters on the stack, how do we actually get them into the libc functions? Turns out it's possible, but it's complicated and it's and so attackers went to a simpler but more powerful technique called return-oriented programming. Return-oriented programming, instead of reusing entire functions at a time, goes, oh, I don't need to actually reuse an entire function. I can simply reuse a little bit of code followed by a return. Now what this return does is it lets the attacker thread back, control back onto the stack, to look at the next value on the stack and say, where do I go from here? So instead of executing the program normally, the attacker puts the addresses of each of these gadgets onto the stack. This was pioneered in 2007 by Shopper. If you're interested in the original work, I highly recommend it. It's a good read. But here's how it works. And I'll go through a simple example. This is the same vulnerable code, but I'm going to use it a little bit differently. Instead of returning to libc functions, or doing buffer overflow, I'm going to actually return to small gadgets. So we have call to a vulnerable function. Again, the attacker overwrites. So in this case, the attacker has overwritten the buffer, the RVP, which we don't care about, the return address, and then some more stuff. And here's how it gets used. The program continues executing and gets the first return. The first return points to this little gadget right here. Now this gadget is just somewhere in the program's code. It can be in the same code as the actual program. It can be in a library that's imported into the same address space, somewhere in the text section. But we've got a simple gadget that pops a few values into registers. This is great because it allows the attacker to take control of parameters to pass to a function. So we return to our gadget. Our gadget first pops RDI, which is going to be the shellcode address. So we're still going to go back and use old school shellcode. It's a lot easier than doing these code reuse attacks, but we need to set up a few things first. We set up the address first into RDI. We set up, the length into RDX, and we set up which memory protection we want into RCX. Now the goal of this little attack is to call a function called mprotect. What mprotect does is it lets the program change memory permissions on page memory. And as I mentioned way back, we don't want readable executable memory, we want read, write, and execute, so that we can write some shellcode onto a page and then immediately execute. So, RDI, RDX, and RCX happen to be the first three parameters that we pass to mprotect. It takes three parameters, we're set. We return, and now the next value on the stack is actually the pointer to the next gadget we want to call. It's somewhere else in the code section. And in this case, all this bit of gadget does is call it. mprotect will then allow us to execute this memory that we put our shellcode into. And then when this returns, it's going to return straight into our shellcode that's going to give us control of the machine. Okay. Questions? So that's your basic ROP attack. What you're actually going to use a ROP attack for is a stage 0. It's going to be an initial vector on a machine that lets you get to standard old school shellcode. ROP is too complicated and annoying. While it's possible to do your entire attack using code reuse, you wouldn't. In practice, you would just inject the code. So, in practice, there's a lot of gadget scanners. Q and Mona are a couple that come to mind. ROP is another one. That will scan through an executable or a library and will tell you, hey, this is a useful gadget, you can use this. There's even some work on gadget compilers that you can write a high-level description of, I want my attack to go and call mprotect with these parameters, and it will actually compile your high-level description down into a sequence of stack addresses that performs these functionalities. Okay? Questions? All right. What do we do about this? This is a serious problem, and we can't do something simple like dep or writable or XOR execute memory. That's a great feature implemented in hardware, but it only works to prevent buffer overflows. So what can we do? There's 4 major categories of defenses against code reuse attacks. The first one is diversity. And this is ASLR, if you guys have heard of that, as you probably have. Second is memory safety, sandboxing. Third is control flow integrity. I'll talk about that in a little bit. And the fourth one is kind of a catch-all category for monitoring behavior of the program. So, what are these things? Well, diversity is a catch-all term for things that make the code look different to the attacker. So we want to mask critical information, such as the location of code in memory. To perform a ROP attack or any code reuse attack, you need to know exactly where each gadget or function that you want to reuse is located. Maybe we want to protect code contents. We assume that the attacker can figure out where stuff is located by side channel attacks or something, and we want to protect what's inside it by masking it. Maybe we want to mask code addresses so that the attacker can't find pointer leaks to figure out where code is located in memory. So the first major implementation of diversity, which is very widespread now, is called ASLR, Address Space Layout Randomization. This is implemented in all your major operating systems now, and what it does is it shuffles libraries around when the program gets loaded. So normally, in the old way of doing things, the program would be loaded as a given address, and each library would be loaded at a fixed given offset. That's a problem when you want to reuse code. So ASLR simply takes a library that's been compiled, position independent, so you can put it anywhere in the address space, and at runtime it picks a random address to put it in. Unfortunately, it's not really random, but it's getting better. And on 64-bit, it's pretty good, actually. So this works like this. Instead of loading the text section for a library, at the old offset, we move it, and now when the attacker tries to reuse those bits of code, they've been moved out from memory. The problem is, even with 64-bit where you have lots of entropy, an attacker can still find a pointer in the memory space. Say the attacker can read some of your heap. You're running a browser, the attacker has control of JavaScript, and finds a vulnerability, a memory disclosure vulnerability, to read some of the heap. This heap is going to contain pointers into the code section. If the attacker can find a single predictable pointer that's always pointing into the code section somewhere, the attacker can go, oh, well, if this points at this offset, then I know where the beginning of that section is, and I can relocate my entire attack. And so that's what people do. So, to combat this, there's been some research into how can we do this at a finer grain level. ASLR is diversity at a very coarse grain level. We move an entire library up and down. But what if we can actually permute the code inside the library? In this case, we've permuted the code inside the text section to move the two gadgets, but kept the library at the same offset. This can be combined with ASLR to make things even harder for the attacker. But now the attacker can't rely on a single pointer. If the same pointer leaks, the attacker still doesn't understand the memory layout of the rest of the section. It's been randomized underneath it. There's many different ways of doing this. All of them that I know of are in the research space. I come from academia right now. And so academia has been working on this pretty hard. And I would love to see some of this actually implemented in industry. If you're interested in that, come talk to me. But the major ways that academia has seen to do this is with a compiler. At the compiler level, when you compile your code, you can compile any different versions and give out a different version to each user. Now when the attacker tries to look at his own version and attack someone else's version, the versions aren't going to match up. The code's not going to look the same. And so these code reuse attacks are going to fail. Another variant is doing this in the linker. So OS security through fine-grained address space randomization is a nice paper if you want to read a paper. But they actually do this live re-randomization. So while the program is running, or the kernel in their case, they actually take the entire program and re-randomize it periodically. This is correct. This means that if the attacker can try to divulge some areas of the code, it gets moved out from under. But unfortunately, it's implemented on microkernel. It really isn't practical on, say, Linux or Windows. The third way of doing this is dynamic rewrite. This means you don't need to have access to the source code, you don't have to recompile your program, but it means you have to run it through a rewriter that tries to read the x86 code, disassemble it, and then rewrite it to look different. A couple of the more practical ones in this is binary stirring and oxymoron. If you're interested, take a look at it. War Tortel actually was a guy that did some of the binary stirring work. Awesome stuff. So these actually rewrite object files or executable code during load time or on disk before it's loaded. This allows the end user to have control over how the code's rewritten and randomized, but is a little bit more complicated and comes with a little bit of overhead. So that's diversity. It works well, but we'll talk about a couple of attacks in a little bit that target it. The next defense is memory safety. Memory safety, you might be more familiar with the term sandboxing. Who knows native client? It's pretty popular, Google's using it in the browser. It's a form of software fault isolation, or sandboxing. Apparently they hadn't invented the word sandboxing yet, so they called it SFI way back in the day, and it stuck, unfortunately. So this rewrites all of the code so that memory accesses are now safe. They don't go outside of bounds that the sandbox declares. And it checks all of the indirect control flow transfers. These are the control flow that the attacker might be able to modify. Things like return addresses, where the attacker can overwrite the stack and modify where the return address is pointing. Things like indirect jumps, where the jump takes a address out of memory. The attacker could overwrite that memory, it's writable. So sandboxing has to put checks at all of these indirect control flow transfers to make sure that it doesn't escape the sandbox and that the attacker isn't able to control code execution. This comes with some overhead, and it requires some compiler support to do it well. So, of course, security engineers don't like overhead. We don't like things to be slowed down. So, control flow integrity is a subset of what sandboxing does. Rather than preventing all memory errors, we can just check all of the indirect control flow transfers. So we allow the attacker to overwrite control flow pointers, but then we check them before we actually visit them. This is, and unfortunately you can't see the reference. I will put these slides online sometime, so ping me on Twitter or something if you aren't. But Abadi et al. Did this in 2009. It comes with some overhead, but it gives you safety guarantees that the code will not execute outside of its normal control flow pattern. So the attacker can't hijack the control flow and perform code erasing. Unfortunately, 21% is still too high for a lot of people. So academics were like, oh, well, we don't really need to do full control flow integrity. We'll just check that every destination address that we jump to is preceded by a call. So every time we return, we'll just check whether there was a call right before it. This seems pretty reasonable, right? How is the attacker going to be able to perform a code reuse attack when it picks out gadgets that are completely preceded by calls? Well, it turns out there was actually 3 different papers in the last couple of months doing this exact attack and showing it's practical. So they actually performed ROP attacks where all of the gadgets that were used were preceded by a call instruction. So every time this partial CFI would check, hey, am I going to a place that was preceded by a call? Did I actually get a correct return address from the stack? The attacker can make this, fool these systems and make them look like they're legitimate control flow transfers. So this doesn't work. We have to go back to full CFI with 20-some% overhead. And a final category of defenses is runtime monitoring. So these previous defenses are all ahead of time things that work either when the program's compiled or when it's loaded to try to prevent ROP attacks from being executed. In terms of control flow integrity, there are checks at the indirect control flow transfers embedded in the program. Well, runtime monitoring is a catch-all term for things that look at the program every once in a while and check to make sure that it's operating properly. There's been quite a few of these proposed. Microsoft ran a Blue Hat challenge not too long ago. I don't know if any of you have heard of it, where they put out a challenge for, hey, give us some sort of ROP mitigations. Turns out that they got quite a few. And they put one of them into EMET. But these runtime monitors rely on heuristics. They rely on taking a look at how the program's executing and figuring out, oh, has the program performed n returns in a row? So say, has it performed 8 or 10 or 12 returns without doing much in between? Or has it executed a bunch of small little code segments that look like gadgets. This is usually done with support from the processor using the branch trace registers, or last branch registers, branch trace registers, sorry, which is a little debugging extension in Intel processors and now AMD, which allows someone who's debugging the program to look at the last, say, 8 branches the program took without introducing any runtime overhead. This is great, but it allows these runtime monitors to only look at a small snippet of program execution. Turns out that in practice, these heuristics are all bypassable. There's another couple of papers bypassing these. If you're interested, look at Usenix Security this year. Some great papers there. But they all rely on heuristics, and these heuristics cannot be tightened enough to prevent bypasses. So the heuristics, if they were tightened more, would catch legitimate programs. So, where does that leave us? Well, I'd like to talk about a couple of new attacks that have been introduced in the last couple of years that resemble ROP attacks for the most part. And often, a couple of these are ROP attacks. But they do things in a slightly different manner and are a lot more dangerous. I'm not convinced that these are practical, only that they're interesting. So the first of these is just-in-time return origin. This was a fun paper from last year. Hey, the citation guidelines slide. This relies on a huge set of prerequisites. First of all, it relies on having some sort of scripting language that the attacker can control, say JavaScript in a browser. Then it relies on a memory disclosure that allows the attacker to read any byte in the program, any byte in the address space. So the attacker picks a byte or picks a page of memory and can read it from this dynamic scripting language. So what this attack does is it actually finds code pointers on the heap through this memory vulnerability. It then follows that code pointer and reads this page of code that code pointer points into. So if you recall, memory protections can only be implemented in hardware at the page level. So it's safe to read an entire page of code if there's a code pointer in it. Then this dynamic scripting language, JavaScript, can disassemble this actual code page, so the x86 on this code page. It doesn't rely on actually knowing anything ahead of time. It simply looks at it at runtime and assembles a ROP attack from these code pages and snippets of code that it can figure out at runtime on the fly. This is crazy complicated. I'm not convinced that it's actually a practical attack, but it's feasible. They demonstrated this against Internet Explorer, and it's a very powerful threat line. So if you assume that your attacker can read everything, then diversity doesn't do anything. Masking the code doesn't really help. So what can we do? Well, there was an interesting paper, again from UC Irvine, on a defense. So the JIT-ROP attack relies on following code pointers from page to page. So if you get one pointer, you get one page of code, and then you disassemble that page and look at any jumps or calls from that page to a different page. Now you know another code page. You keep recursively doing this until you assemble enough code that you can find all the gadgets you want to find. So what oxymoron does is it prevents the attacker from recursively following these code pointers. I have a picture for that. Hopefully you guys can see in the back. If you can't, that's fine. But the attacker leaves a pointer, say into page 1, and then disassembles this. This is in the normal case without any protections. It's the attacker sees, oh, you make a call to some address, 1122. Okay, well I'll go read that page too, because that must be a code page, and I'll disassemble that code page. And then the attacker gets more and more code and proceeds to find all their gadgets. Well, what oxymoron does is it uses a super old trick that the memory manager used to use in x86. It's still around, backwards compatibility and all. This is called the segment registers. What segment registers do is they allow you to add an offset. So if you see this FS, that's a small register in the processor. You set these up with a little table, and they like to add arbitrary offsets to memory addresses. So in this case, we want to add an offset and grab the code pointer we want out of a big table that we put protected behind the segment register. Now the attacker can't read the segment registers. The attacker can read memory pages. The attacker can read maybe the stack. But the attacker cannot read arbitrary registers before they have arbitrary code execution. So that means the attacker doesn't actually know the contents of FS. But the program, every time there's a reference from page 1 to page 42, in this example, the program indirects this through a table where it actually looks up the destination address in this table. The table is placed randomly. The attacker won't be able to probe forward and find it in a 64-bit memory space. So this allows all pointers from page to page to be masked with this FS register. Unfortunately, there's still some ways to get around this. Maybe you can find a whole bunch of pointers into individual code pages, disassemble those, and so on. But this is a great defense in terms of protecting against your code. It really raises the bar. A second attack, I don't know if you've heard of this one, but this was a really fun attack that some Stanford guys did. And what they did is they said, oh, well, we don't actually care what your program looks like. We just want to find some stuff in address space. We want to find these gadgets that are using this. So we can just brute force through your address space. Servers like Nginx tend to fork processes to handle incoming requests. If these processes die, Nginx happily forks you a new one. So what you can do is you can actually probe and jump into the code at random offsets until you find something that behaves the way you want. In their case, they found a single gadget that loaded some registers from the stack. Remember I showed you the pop, RB, pop, and return gadget? They go and find that very same gadget, actually, based on its effects. The way they can do this is they actually probe the procedure linking table, which is just the table of library functions in a process. And they probe it for a sleep call, or something that behaves similarly. So there's 3 states that the blind ROP attack could have after it runs an iteration. It can either crash the program. This is going to happen if it runs into some code where the program seg faults or has some sort of fault. It could hang and not come back with a response. Or it can come back with a correct response, give you the website. What you can do is you can go find, by random probing, some gadget that operates like a sleep. It just hangs. And then with that, you can actually probe for other gadgets and construct your ROP attack on the fly with no knowledge of what the program looks like. They did this against a toy service where they had never seen the source code, they had never seen the binary, but the attack still works. It's a little bit finicky, but I think this is a very, very powerful attack. The solution is don't allow step 1. Don't allow forking of services willy-nilly when they're crashing. GR Security does a great job of protecting against this. If you're not familiar with GRSec, go become familiar with GRSec. It's a great piece of software. And so they have an option for doing this. The way this looks in practice, like I said, same vulnerable function. But now we're just going to try randomly probing into the code space until we find, oh hey, we found a sleep gadget, something that calls sleep. We can now have this third state where we say, oh, well, we call some random address and we call sleep and we see if the program slept. If it crashed, we know that's not the gadget we're looking for. If it didn't crash, we know, hey, we found useful. So, blind ROP is an awesome attack. It's kind of scary, but don't worry, on Windows, this is not a problem. Windows process creation actually reapplies ASLR. You can't fork a process with the same memory layout. A mitigation for blind ROP, as well as ROP attacks in general, that I've been working on, so if you're interested in this, come talk to me, is something that I call booby traps. Rather than just simply randomizing the code and making the layout look different through ASLR diversification of some sort, I want to actually do that, plus insert small booby traps that catch the attacker's execution and allow us to respond to it. These booby traps would normally never be executed, they get skipped over, but then when an attacker is randomly probing for gadgets, or tries a ROP attack that he thinks will work against your target system, they instead might hit a booby trap, the defender gets control of the process, and gets an alert saying, hey, something very seriously wrong. Please go fix this. You can even do some fun things like disassembling the attack by looking at the instruction pointer and stack pointer and reverse engineering the attack automatically, because you're actually in the middle of an attack in the program's address space. You don't have to take memory notes. So, where have we come? We've come all the way from buffer overflows in the 80s and 90s to code reuse attacks to being able to do code reuse attacks against arbitrary code you've never seen in your life. So I think as we go on, it looks right now like attackers are winning. We'll see how this plays out in the next few years, whether large-scale diversity or large-scale CFI gets implemented. But I would highly recommend, if you're looking at application security, to take a look at a few of these defenses and see what you can do. Questions? Yeah.
Has anyone looked into rewriting the virtual memory mapping on after fork, so you get a keep copy on write, but you still have re-randomized addresses?
Yeah, I know a couple of people that are looking into that right now. Nobody has published anything to my knowledge on it, so there's nothing like concrete. But I think it's perfectly viable to do. The problem that you have with that is programs assume the same memory layout. So they assume that if I take an address in the parent and then pass that address to the child, that address is still going to be viable.
If you use PIE though, and that would be offset.
I can take an address of code and put it in memory somewhere. And this actually happens. Things like vtables. Vtables are tables of code pointers. The fork would actually have to rewrite all code pointers in the child process, which is possible to do, maybe. It would be non-trivial. Questions on like practical aspects of ROP attacks. You mentioned, do you want to repeat what we were talking about earlier? I'll go into a little more detail.
Well, actually, where do you go for the latest information?
Where do we go for the latest information? Well, I'm a grad student, I read papers. And I would recommend actually reading some of these papers. So, application security, system security papers tend to be fairly readable. They usually start with very long intros of, here's what a code reuse attack is. Which if you've seen them, they get a little repetitive. I would go read some papers. A lot of blog posts tend to be useful. I've seen some very good ones, I've seen some very bad ones. Other than that, there's not a whole lot, man. All the stuff is pretty good. So, USENIX is a conference, all of their proceedings and their talks are online. So if you're interested in some of this stuff, go back through, USENIX Security is the name of the conference. That's a very good one. Go back through some of those and watch a couple talks. They'll at least get you on the right track. Watch the blind ROP attack. Blind ROP attack talk. That's called Hacking Blind from this year's. No, I'm sorry, it wasn't USENIX, it was IEEE. That was not going to be on there, which is very, very unfortunate. But that's where I would go. A lot of the stuff that I've seen in code reuse is actually happening on the academic side. Most of the practical attacks using ROP are simple, hey, let me bypass ASLR, let me bypass DEP, and then get you shut. So yeah. Other questions?
I read a bunch of the GR security papers, and it seems like the mainstream Linux people hate them. So the question is, what's it going to take until their ideas get generally accepted in the Linux community?
There's a fight right now between GRSec and a couple of other patches that do similar things. Yeah, I don't think it's going to happen because of personalities. I think it should,
Right.
but as far as practical personality-wise, I don't think it's going to happen.
So we're screwed.
Or you can go apply GRSec patches. Yeah, there's a lot of, so the fights that I've seen is from, oh yeah, I'm blanking on
The
the,
PAX team?
no, PAX team is great, but most of that stuff is out of date now. So PAX is basically this writable XOR executable patch I'm talking about, which is in the mainstream kernel. It's in the mainstream kernel, it's supported by hardware, no problems. So I wouldn't actually recommend PAX, simply because if you're on modern hardware with a modern kernel, it doesn't. But what?
Brad Spangler?
What's up?
Brad Spangler? GRSec?
No, that's the guy. Yeah. No, I'm thinking of the Linux permissions, the extended permissions. Why? Anybody? The whole crazy extended permissions. I'm talking about SE Linux. Yes. So SE Linux and GRSec are competing right now, and SE Linux is in the kernel. So I don't think GRSec's getting there.
You mentioned Emmett.
Yes.
If you find stuff that works, you can also get those protections turned on.
Yes.
Not just ASLR. And I know that Romy wrote a paper, I think, that was bypassing for one point, version 5. It's not perfect protection, but you guys make it fairly.
Emmet is great. Emmet really raises the bar. It's things like, I think Rockard was the one that made it into Emmet. I forget, don't quote me on that. One of these runtime monitorings in there. You can force ASLR on programs that don't enable ASLR by default, which may or may not work. So yeah, Emmet's great, but there's bypasses. I've seen V5 bypasses. Yeah. So, as far as practical recommendations, enable Emmet. Enable ASLR if you're on Linux. Go check your programs. Go look at Firefox. Does it enable ASLR on